Thanks a lot for the opportunity to present my work here. And today I'll be talking about, as the title suggests, patterns related to tropical planar curves. And then that led to some of our work delving into a certain class of lattice polygons, which we eventually named as panoptigons. So just to give you a brief idea of what all we'll be talking about in this talk. So firstly, briefly, I'll introduce the central theme about what are these forbidden patterns, and these are related to metric graphs, which we'll call as skeletons. And I'll talk about what new forbidden criteria or patterns we were able to find out and what do they actually forbid. And eventually, then the second part of the talk would be dealing about panoptigons and defining panoptigons, and then classification and enumeration result that we were able to prove. And subsequently, we'll try to stitch back the connection which led us to inquire about this class of lattice polygons and how this connects back to the story of skeletons and tropical curves. And eventually, as time permits, I'll also talk about certain future problems and where all these problems have led us to. So let's just introduce what would be the central theme. So for us, a tropically planar graph is a metric graph G, which is dual to a regular unimodular triangulation delta of some lattice polygon P. The central question that we are dealing with is which graphs G can occur in this way. And so I'll try to take your attention to the picture. So this picture actually encapsulates almost all of the discussion that we'll be having. So you'll start with the lattice polygon, and you'll be having a really nice unimodular triangulation. By unimodular, you mean that the normalized volume is 1. In this case, we'll be planar, so all the area of the triangles is half. So you get this really nice unimodular triangulation. And in tropical geometry, there's this well-known notion of duality. So dual to this subdivision, you have this tropical curve. So you can see each edge being dual to another edge present in the subdivision. And interior lattice points correspond to cycles. So this point corresponding to this triangle. And likewise, you have 4 interior lattice points which correspond to 4 triangular cycles in this graph. And then there's a nice graph theoretic operation that you can conduct on this tropical curve in order to retrieve this metric graph, which we'll be calling the skeleton. So in our story, we start with a unimodular triangulation of a lattice polygon, look at the dual tropical curve, and produce the skeleton via a graph theoretic operation. The graph theoretic operation is pretty simple. So you first delete all the degree 1 edges. So obviously, these are going to infinity. So you delete all these edges, which are going to infinity, and then you get a degree 2 node in your graph, which you just smoothen out. So first you delete all degree 1 nodes, and then you smoothen out the degree 2 vertices or nodes. And what you're left with is a trivalent planar graph, which we'll be referring to as the skeleton. So as you can see, this need not be simple, as is the case. Loops and bi-edges are allowed, and this graph is having 3 loops. So we are interested. So given a certain number of vertices, we already know how many graphs up to isomorphisms are present there. So here, if you start with genus G, you know that you get a graph on 2G minus 2 vertices and 3G minus 3 edges. So with already a nice classification of isomorphic graphs, you want to know out of all, for given G, out of all graphs, how many can occur via this process. And I'll try to make this more precise as we move forward. So the duality that I was talking about condenses in this format. So if you have a tropical curve C, then that corresponds to a regular subdivision of a Newton polygon P. And we are considering the smooth case, which corresponds to unimodular triangulation. Hence, in my cases, all subdivisions would be, first of all, triangulations, and then again, they'll be unimodular. So one of the invariants that is of importance here is what we call as the genus, and it corresponds to the number of cycles present in your tropical curve, and that corresponds to the number of interior lattice points that were present in the lattice polygon. And here you can also see that you can define this skeleton in terms of topology as well, as this metric graph uh, is the one that also allows a deformation retract from your tropical curve. And again, this one, the skeleton also has G many cycles. So as you saw, there were 4 cycles present in your tropical curve C, and in the underlying metric graphs also there are 4 cycles. And the genus in this case is 4. So the work begins with in this direction. One of the first papers was in 2015 in Sarah Brodsky, Michael Joswig, Bernstrom-Fuld, and Ralph Morrison studied the modelized space of tropical plane curves. So this is so there is a modelized structure where, as I mentioned, there are these 3G minus 3 edges which are present in this graph, and people were interested in order to know that do you have the dimension of the space as 3G minus 3, or is it reduced once you look at graphs coming from this convex essentially operation? And that turns out to be true. So in this paper, there are many other results concerning this modelized space, but essentially they wanted to construct this modelized space explicitly for lower genera, essentially 3, 4, and 5. And what they mean by construction is that it comes down to considering only some finitely many lattice polytopes in order to consider all lattice polytopes. It's sufficient, it's a non-trivial result of Coleman and Walter Kostrick, that you need not consider all lattice polygons with, let's say, 3 interior lattice points. There are certain lattice polygons which they term as maximal, and they are sufficient enough such that you compute the unimodular triangulations of these finitely many ones and go through all of this procedure, and they encapsulate all possible ones that might occur with respect to that fixed genus. So they use that classification. So this classification of finitely many maximal polygons was already known by the work of Kastrick and Voigt, and they had done that for genus 30, but they didn't. So they just started in this paper to use that classification for 3, 4, and 5. And turns out in this picture, as you can see, for the case of genus 3, only a single lattice polygon is sufficient, and that is this triangle. So the problem just boils down to just producing all unimodular triangulation of this particular lattice polygon, looking out at all the dual tropical planar curves and finding all the skeletons, and this all has been implemented in polymake. So the first major result that they were able to find out was that in this case, so in this case, 2G minus 2 is the genus is 3, so 4 vertices. So on 4 vertices, they had 5 graphs, out of which they were able to find that one does not occur. One does not ever occur. So with this first paper, they were actually able to show that there are certain graphs which never occur via this construction, but they were only able to show one criteria which can prove that why that graph doesn't occur. But subsequently for 4 and 5, with their computational enumeration, they had classified graphs which never occurred via this computation, but they were not able to classify them via a theoretical argument that why they can never occur. So this is the central plot of the problem, essentially meaning that for lower genera, can you attack this problem? Given the classification of maximal polygons, start with a lattice polytope, compute all its unimodular triangulation, compute the dual tropical curve, the skeleton, and then just compare it with the known class of graphs and check whether you have encountered all of them. And if that's not the case, then look out at the graphs which haven't occurred, and can you classify them under certain criteria saying that they satisfy certain properties and hence they couldn't show up. So just to point out about the result that they are using. This comes from a paper by the name of Moving Out Edges of a Polygon. So I'm sorry for this. This is just a call bell, and you can kindly just avoid that. Sorry for that. So this paper is in the name 2012, Moving Out Edges of a Polygon. So there's a notion of moving out for a polygon discussed here, wherein you can consider a two-dimensional polygon. In this case, we are always in that case, and consider the convex hull of the interior lattice points as delta 1. And so delta 1 is just the convex hull of interior lattice points, and delta minus 1 is obtained by pushing out these edges of your polygon, which is done by what they call as moving out. So since we are planar and two-dimensional, so if your hyperplane satisfying this edge is this, you move out this edge by just taking the hyperplane is equal to c plus 1. And here a and b were relatively coprime. So you can do that. And what happens is essentially you move out as is shown by the red dotted polygon. Obviously, this need not be a lattice polygon. But one nice thing that happens is if you start with the polygon, consider the convex hull of the interior lattice points, and then move out, then the envelope that you get always contains your initial polygon that you started with. So that's their result. So this delta 1 minus 1 is like considering first the inner convex hull and then moving out. So your original polygon is always contained inside this. And we call polygons where there is equality, we call them as maximal. So this notion of maximal is a bit different, not in terms of area. So this is the crux of the argument that was used for this classification, the classification of maximal polygons. So these are those polygons for which this equality is there. And the classification up to genus 30 was already there before this work of Trotsky and others. So let's just have a glimpse of what the problem looked like. So as I mentioned, in the case genus 3, you only need to consider this triangle. And this triangle has 1278 regular triangulations. And as I mentioned, the 5 graphs on 4 vertices. So these are all 5 graphs that can occur on 4 vertices. And turns out the one marked with an asterisk, that this never occurred in their computation. And so this is what this graph was termed as sprawling. So sprawling is a graph such that sprawling is a trivalent graph such that there is a vertex such that all edges coming out of it are cut edges. So in this, all 3 are cut edges, and hence this graph is sprawling. So if you see the case for genus 3, it's completely classified, meaning even if I didn't have this computation and I knew that sprawling graphs can never occur as skeletons of tropical planar curves, I could have just started with this family and ruled this out, and already I have a complete classification of all realizable ones that are present. Obviously, this I can say only after I also have the computational enumeration, but it's good to have that it's completely classified, meaning that the criteria that they came up with sort of completely gives you a reason to rule out all the graphs which never occurred. Likewise, as you move to genus 4, you can't work only with one. So you have these 3 that you need to consider. And just to give you an idea of the complexity of the computation, I've just put in the numbers for you. So it's still not bad as it is in terms of computation. Around 6,000 is the maximum number of unimodular triangulations that you're dealing with in this case. And in the case of genus 4, there are 17 graphs, out of which one is non-planar. So obviously being non-planar is the most trivial criteria to be ruled out of occurring as skeleton, because we are working with planar graphs, and 3 of them are sprawling, and all others are realizable. So this is already this result is already there in the 2015 paper. Just as a side note, one should see that troplanarity. Troplanarity is again another way of saying that a graph is realizable in the sense that it occurs as a skeleton of a tropical graph. So a graph is troplanar if it is realizable in this sense. So this notion of troplanarity is not minor closed, meaning that this graph, which we actually saw in the first picture of genus 4, is actually realizable. I showed you a unimodular triangulation realizing this one. But if you consider a minor of this is actually sprawling and not realizable. So one starting side note is that this notion of being troplanar or being realizable is not minor closed, just as a side way. So now coming to the advancements that we know that took place after this initial paper was, so they already knew about this condition of sprawling. And two more conditions came to be known as, one is TIE fighter. So I guess all Star Wars fan can get the connection here. So this looks like the TIE fighter plane in the movie. So there's nothing much more to say. If your graph is actually looks like this TIE fighter, meaning the shaded portions are graphs of positive genus, are subgraphs of positive genus. So you can have any attachments going on here. It's just the basic structure of your graph looks like this TIE fighter, then that can be ruled out as never occurring. And the one in between represents crowded, which means that you will either, in all planar embeddings that you consider, there might be two faces which share two edges in between them, or you have an embedding which shares a face with itself. So here in this case, this is a family of crowded graphs where you can see that these two faces actually share two edges in between them. So hence this family of graph is crowded. So this is already, these criteria were already known. However, what was known, since in the 2015 paper, the computation was done till genus 5. So they were able to rule out some of the graphs which never occurred in their computation. They knew that they never occur, but they weren't able to furnish criteria which could govern that why they are not occurring. So again, just some definitions about subdivisions. So there's a nice subdivision which is known as split, which is a subdivision which contains exactly two maximal cells. So it is one of the coarsest subdivisions that you can have. And a nice property about these splits is that the cut edges in your skeletons correspond to these splits. And two splits are compatible if they're split lines. So essentially, since we are in the planar case, so you can consider the hyperplane along the edge of the subdivision, and that is your split hyperplane. And if your split hyperplanes do not meet in the interior of your lattice polygon, then two such splits are said to be compatible. And turns out in our case, the splits corresponding to distinct cut edges are always compatible. So these are some technical info that we'll be using in most of the proofs of coming up with new forbidden criteria. So beginning with one of the first results that we were able to show was that we introduced a new structure called as heavy cycle. So a heavy cycle of a graph is this cycle C that you see in this graph, this cycle. And if your graph looks like this, wherein you have a cycle C like this attached to two components G1 and G2, along with a underlying component G3, then we were able to show that the triangular faces, so each node in the graph corresponds to a triangular face. So this would also correspond to triangular faces in your subdivision. These two, so the crux of the lemma here is just saying that the triangular faces corresponding to the nodes V1 and V2 would actually share an edge in between them. So since they are part of a cycle C, so they obviously share a vertex. But as I mentioned, the graph theoretic process, it might happen that there are degree 2 triangular faces which eventually get concatenated. So that the theorem is just saying that that's not the case. So they actually share an edge and there are no triangles in between them. the triangular faces which correspond to the nodes V1 and V2. And it also additionally just says that so these are cut edges in the graph which corresponds to splits. So the remaining sub polygon which would realize this G3 union C subgraph would be hyperelliptic, meaning hyperelliptic polygon in our case just means that the interior lattice points lie on a line. So the convex hull of the interior lattice points is just one dimensional. So in that case, lattice polygon is referred to being as hyperelliptic. So in this case, we refer to the subpolygon which realizes this subgraph as the heavy component as well. So that is just one nomenclature. So the whole lemma just states that the triangular faces corresponding to the nodes V1 and V2 actually share an edge. And the proof just begins with taking the contradiction and assuming that they just share a vertex like this and arguing with our with convexity that that cannot happen. So in one case, we consider that the split lines, the split hyperplanes are parallel, and in the other case, they intersect at a point. And then we argue in both cases that both these cases cannot occur, and hence we are able to get these technical results. So the first criteria that we were able to show using these technical know-hows about splits and the heavy cycle lemma is the one that you see in this picture. And we refer to such a structure of a graph as a sprawling triangle, which is very similar to a sprawling graph. It's just that the node is replaced by a triangle. And the criteria that we show is that if your graph has a sprawling triangle, then the only case in which it's realizable is the one that I showed you in the first slide, is the case when all these subgraphs are loops. Essentially meaning that if you, as soon as the genus increases of more than increases from 4, then such a graph can never occur in the procedure that I mentioned. So this is one of the first criteria that we were able to show. And another criteria that we came up with is an extension coming from the technical result of the heavy cycle lemma. So this just says that when the subgraphs that we showed previously are just loops, then in this case, the subpolygon realizing this part can have at most 3 interior lattice points, and the subpolygon is hyperelliptic, meaning all the interior lattice points in this subpolygon have to lie on a line. So the proof just uses now the fact that we know of the heavy cycle. So now we can consider triangles, but now as you can see, they share an edge. And then again, arguing via convexity, and given the fact that these subpolygons just have a unique interior lattice points, we are able to show that given this constraint, this is the lattice point, which is the interior lattice point, that can only be the interior lattice point. And again, here in this is the only lattice point that can be the interior lattice point. And with these constraints, you realize that the interior lattice points can only occur on this line. So hence, whatever the subpolygon is hyperelliptic, first of all, and secondly, then we argue that it cannot go beyond 3. So again, what happens with these two new criteria? So with these two new criteria, so before our results, these 4 graphs were yet to be categorized under a criteria. So we knew that they can never occur, but they didn't come under any criteria that was known prior to our work. But with our work, we were able to provide a complete list of criteria such that if you look at the 71 graphs that are possible for this genus 5, you can classify all of them and rule out all of them which lie under with the list of criteria that you already have, meaning either a sprawling node, either a sprawling triangle, crowded and TIE fighter were already known, and the heavy cycle with 2 loops result also rules out these 4 graphs. You can also see it depends. You can also rule them out with the sprawling triangle as well. So there is some sort of an overlap. It depends on how you want to look at them. So essentially, this was one of the major takeaways. And for genus 6, this was the picture that was left to us. So these 8 graphs were left, apart from like, so there are 388 graphs that are all possible, and after all the exclusion in terms of the criterias and whatnot, you were left with these 8 graphs after our first results. And so this was the state of the art in terms of till 2020 in terms of knowing about skeletons. And then in a subsequent paper, I was able to push these results for genus 6 as well. So earlier we provided a complete classification up to genus 5 and were left with these 8 graphs. And I call this graph env loop. It's sort of a envelope and a loop. So this graph I refer to as envelope. So if you just take this one out from the 388, all others can be ruled out. So I didn't feel the need to maybe add one more criteria just for one graph. So the framing of the graph of the statement is if your graph is not in the loop to begin with, then all others can be ruled out. And the new criteria that were needed in order to complete this picture was some sort of extension of our results, but claiming that in this case we had a heavy cycle but with 2 loops, but you can also consider with 1 loop and allow the other one to have arbitrary genus, and then just look at the specific case. So again, we were able to show that for arbitrary genus, again the sub polygon realizing this part of the graph is again hyperelliptic. But in the case, if you refer to the case for genus 6 and the genus of this component to be 2, then in this case this component is also hyperelliptic, and this triangle and the triangulation restricted to this subpolygon cannot have a non-trivial split. By a non-trivial split, I just mean to say that you can't have a split edge such that it divides your polygon into 2 parts such that one of the part doesn't have any positive genus, which maybe I can show you in one picture. So this is one nice example. So in order to see the splits, so these are the splits. This is the split edge, and this split edge corresponds to this cut edge here. And this is one very long split edge, if you can see. So split edges are also nice because both the endpoints are on the boundary. So you see this unique edge present here. So this is the long split edge which corresponds to this cut edge. And likewise the duality for the whole graph. So this is an example for genus 6 graph, which is actually realizable. But the main takeaway of the result is that this graph is realizable. However, there is another graph wherein this genus 2 component is just of the form of a bi-edge and a loop, and that is not realizable. And the unique triangulation that would have realized that would need to have 2 non-trivial splits because you have 2 cut edges, one here and one here. So there has to be a non-trivial split in the subpolygon which realizes the genus 2 component, and I just show in this result that that cannot be the case. So that is the takeaway to rule out all these graphs, and that is again arguing by convexity, and you can show that there is a maximal polygon in which all such polygons will exist, and in no matter in any subpolygon you cannot have a non-trivial split. Is there a question?
Is there a question? No, it seems not.
Okay. So this is just to give you a picture of how these split edges are actually present in the subdivision and how they correspond to cut edges, and just to give you a glimpse of what this result was talking about. So we already had the heavy cycle with 2 loops, and with certain restrictions we were able to consider the case for genus 6 and were able to rule out some of the graphs. And again, a similar result to the heavy cycle, we were able to show that if you have a double heavy cycle, so the technical result that we had earlier was that if you for the time being do not consider this middle edge, so we showed that the triangular face corresponding to V2 and V1, they both shared an edge. And now we just say that the 3 triangular faces corresponding to V2, V, and V1 all actually share an edge between themselves, something like this. So these two share an edge, and then these two share an edge. So all three consecutively actually share an edge, all these three triangular faces. And the proof is similar to the heavy cycle lemma. And with this, the technical result about double heavy cycle, again, similarly, we were able to get a result about double heavy cycle with two loops. So here, earlier you had some graphs of arbitrary genus, but now we consider only just a loop, which is just a unique uh, loop and a unique interior lattice point in the subpolygon. And the result that we get here is that the subpolygon realizing this graph has the convex hull of the interior lattice points is a unit parallelogram. So here it's a bit slightly different. So earlier, as you saw in the heavy cycle, it was always hyperelliptic. But in the double heavy cycle case, we can't say that it's hyperelliptic. However, we know that it's the convex hull of the interior lattice point is a parallelogram. So it's no more hyperelliptic, but still well within constraint for the case when the genus of the whole graph is 6. So as I mentioned, so the idea was to push the classification that we already had for uh, uh, genus up to 5. And with these two new criterias, mainly heavy cycle with one loop and double heavy cycle with two loop, we were able to finish the classification for all. As you can see, it's a bit, the statement gets a bit loaded at this point. And yeah, you have to take out that graph which I mentioned, which I call the NV loop. So apart from that, out of all 388 graphs, you just start with already the prior known ones and you rule all of them out. And eventually you'll only be left with the graphs that are actually realizable. So just before moving to a side note, I would like to also mention that this, so there is a result saying that as the genus increases, we now know of a result, as the genus increases, you'll have a lot more troplanar, a lot more graphs which are actually not troplanar. So essentially, there is a result by Ralph Morrison now, which we know that eventually you'll need a lot of, like, it's not possible in terms of the family of all graphs. You can get infinite graphs which are actually sprawling, and likewise for other criteria. So, like, it's not possible to, as the genus increases, you cannot furnish a complete classification since you'll be getting a lot of new criteria. So in terms of lower genera, this is still possible at the moment, but as soon as the genus starts increasing, then you'll need to have a lot more new criteria, and then also you won't be able to furnish this. So hence, this is in terms of what we know at this point. So at this point, we have uh, the complete picture for genus 6. However, even in terms of computation for genus 7 and beyond, this is now at the cusp of what computational power that we have. Essentially, you have 2,500 graphs, and the polygons also have a really large number of unimodular triangulations, which is beyond at least the capabilities of the programs that we have at the moment. So just a side note, which we eventually saw in the first picture that we saw. So there is a nice collection of triangulations that we were able to encounter, which we refer to as anti-honeycomb. So the picture that we saw in the first slide, which gave us this skeleton. So this picture actually resides here. So you can just see that triangle here, and that is just copied in the sense. So you can consider these three family of parallel lines, essentially these ones and these ones. And then there's another one. Yeah, this one. So these three families of parallel lines can give you, in terms of a parameterization of these certain anti-honeycomb polygons that we consider. And the name anti-honeycomb is coming from a parallel class of honeycomb polygons, and which correspond to skeletons having honeycombs. Sorry for my drawing. So they correspond to honeycombs. And so these, as I mentioned in the 2015 paper, there was another aspect. So I'm just giving combinatorial obstructions for realizability at this point, but I'm not talking about the metric. So as I mentioned, these are metric graphs. So each edge also has an edge length data associated to it, so which can define the dimension of the modelized space of metric graphs, essentially. And one nice result is that the maximal dimension of this space mg, is 2g plus 1. So you had 3g minus 3 edges. However, the dimension is only 2g plus 1, which is much less. So like if your graph is realized through this process, it loses a lot of dimension. You had choices of a 3g minus 3 random length, but you only get 2g plus 1. And these are supported on honeycomb triangulations. So the graphs which actually have dimension 2g plus 1 are the ones that are obtained via honeycomb triangulations. And the graphs that occur in this case have much less dimension, not the lowest possible, but much less. So hence the name anti-honeycomb. And just a bit of symmetry, in the case of honeycomb also, you can get 3 families of parallel lines and they define a class of similar polygons. So hence the name anti-honeycomb. So we were also interested, maybe at one point we had a question in order to produce like nice symmetric weight vectors for these such nice triangulations. But that was, yeah, just one aspect, and we had some nice pictures to begin with. So that's one segue. This is not a part of essentially like forbidden patterns, but just something we encountered during the process. So this leads on to the second part of our talk. So herein we define what we mean by panoptigons. So a panoptigon is a convex lattice polygon wherein it has a lattice point which can see all other lattice points. So in these pictures, you can see that this lattice point, which is encircled, can see all other lattice points present in your convex lattice polygon. And the dotted line actually shows that, and it doesn't need to be unique. As you can see here, in this lattice point is also seeing all other lattice points present in the lattice polygon. So we define such a lattice polygon to be a panoptigon. And so one aspect was to, if given under certain constraints, could we classify all panoptigons? And if so, then can we enumerate them? So this picture, first of all, the result is that if you have a panoptigon with lattice width at least 3, then the number of interior lattice points are bounded above by 13. So you can only have 13 lattice points. And so the idea for the proof is very hands-on, meaning you stand at the origin. So this is the origin, and you assume that this is your panopticon point, and there is a implicit lattice diameter condition which we fix as 3 for this case. So you have the longest lattice line segment here, and we fix it to be at this point. So all the black points are the ones that are visible, and then just invoking convexity simultaneously, you can rule out a majority of this portion, meaning these dotted lines. And then at the end, you are just left with these black points, essentially, that can all occur. But then you have to choose which ones actually do occur. So it turns out that even with the lattice points that are still left, you have certain constraints, meaning if you choose a certain one, then so you have to divide them in certain families and argue that if one is present, then sort of the other ones do not occur. All of this can be enumerated, and this is what exactly we did. And this is the computation that led us to this result. So by non-hyperelliptic, I'm meaning that the lattice width is at least 3. Hyperelliptic, as I mentioned, is again all the polygons with interior lattice points lying on a line. So here in all the pictures, you can see the point that is encircled is the one that can see all other points. And so this furnished us with these are 69 in terms of totality. And then, as I mentioned, there was an implicit argument of the lattice diameter. So the lattice diameter actually controls the total number of points that can be present in your, it's a square argument, it's bounded above by the lattice diameter. So hence, we implicitly use that consideration to also characterize for the case when the lattice diameter is at least 2. And in that case, it's easy to argue that these 3 are the ones that are left. So we are now bringing in all the cases. So we bifurcated based on lattice diameter, once less than equal to 2 and once greater than equal to 3. So the greater than equal to 3 provided us these 69, and the less than equal to 2 gave us these 3. So up to lattice equivalence, we were able to furnish 72 non-hyperelliptic panoptigons. So we also provide, so there is a computational enumeration as well as the whole argument of how we can rule out the other points that are present in these families that is present in our result. So now one asks, what is the point of studying these convex lattice polygons? And it turns out, so this tells also the question comes from these skeletons. So we define a big phase graph to be a graph such that in all its planar embeddings, there exists a bounded face that shares an edge with every other bounded face. And one such big phase graph is the loop of loops. So the simplest example for genus 3 is this, but the larger ones are just bi edges, each one connected to the other and in a closed loop. So essentially what we refer to as a loop of loops. The striking point here is that in order for such a graph to be realizable, the convex hull of the interior lattice points needs to be a panoptigon. So this is essentially the starting point in order to, which interested us to delve into this classification, because we knew given our computations that such graphs were realizable for lower genera. But as I mentioned, eventually, since all graphs are not troplanar, so given sufficiently enough genus, these graphs would also start showing up as not troplanar. So we considered this family and realized this nice connection to panoptigons, and were looking out for if there is a complete classification for this, and turned out that that wasn't the case, and hence we just built upon this classification, and that turned out to be extremely useful. And this led us to prove this result about skeletons, which just says that if you have a graph, a big phase graph of genus at least 14, then that graph cannot be tropically planar, because if that is the case, then it has at least, then the interior convex lattice polygon has at least 14 points, which can't be the case because it's a panoptigon. And we were also able to consider the cases where the panoptigons are of 12 and 13 points essentially, and move them out to check that whether this graph, whether this bound is exactly strict, and that turns out to be the case that yes, this bound is exactly strict. So this picture just shows you that we considered all non-hyperelliptic panoptigons that we had, which had exactly 12 or 13 lattice points. And then, as I mentioned, this is the interior convex hull, so we can move out, and moving out would give us that maximal polygon. It turns out all of them move out to maximal polygons, which are not lattice polygons. So this in turn is this bound is exactly strict. So some of the future problems that we are planning to attack are one with joint collaboration with Gennady Avakov at BTU Corpus and Ralph Morrison is just the generalization of this panoptigons to panoptitopes. And it's easy to see that if you, the slight modification, such a classification can be connected to really nice families of lattice polygons, mainly hollow, which do not have any interior lattice points, and ones which have a unique interior lattice points, which are also known as canonical phanopolytopes. And there is already some work. However, the ones that we are interested are the half integral polytopes. And turns out that the setup that we use in terms of classification for panoptigons is not sufficient enough in this case, and you'll require new techniques for this classification. So this is one problem that we are currently interested in solving. And another one, which is sort of a work that is going on currently, is talking about chess and thinking of chessboard as a lattice polygon and asking the question. So first of all, the line of attack essentially in chess is again in terms of visibility if you lose the knight, which performs this 2.5 steps. Apart from that, all attacks are in terms of visibility, meaning that your attack piece should be able to see the piece that is going to be attacked in various ways. So there are certain lines of sight allowed. So not all lines of sight are allowed, meaning for the rook, it's a straight line in terms of a straight line in the y and x axes, and then for the other one, it's the diagonal. So sorry, I can't remember all the names for those articles. I know them in my mother tongue, but sorry. So yeah, so I cannot recall the exact names, but essentially the idea is the line of visibility. So now the question is, what is the maximum number of pieces which could be attacked in a single move? So turns out for the 8x8 chessboard at this point, it's the queen article which can attack 8. So not constrained to distance. So the queen is here, so it can attack here, 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 straight up, and likewise. So this is the queen. It has 8 articles which she can attack at any given moment. All the 8 ones surrounding it. So the idea is, how can you maximize, given that you are allowed to choose any convex lattice polygon as your chessboard, and let's just say the queen only has the lines of sight or attack allowed, which are these. But if I allow all possible lines of sight, essentially just visibility, how does this number behave? So there is one answer in terms of panoptigon, which is a slightly strict condition, meaning that in your chessboard, given the queen can see all other articles on your chessboard, at that point that we can bring in the panopticon condition. But obviously this is not the case always. There might be invisible articles present on your chessboard which are not visible. So the idea is so like the panopticon condition would be one point, and then you can sort of start adding invisible boards and see whether this number is always bounded under certain lattice width constraints. Obviously, like as we had a lattice width constraint on even in our panopticon classification, there is a mild lattice width constraint. So obviously all this would be done maybe with slight lattice width constraint and maybe even more, just to analyze this number. So we already know that this number is 8 in the standard chessboard. So but we want to generalize it, so we allow any convex chessboard and try to mimic, because the idea is, again, the line of attack is the line of visibility based on that. And if we can say something about this number, whether it's always bounded above by some number or it grows or something on those lines. And apart from these, some of the other problems that we are interested in is to look at this moving out notion. So in this moving out notion is only mentioned for polygons, but we can also look out for the case what happens in 3 dimensions, because this is also interesting in terms of tropical geometry as well, because as you saw that the study was done for only smooth and planar. So what happens if we relax these 2 conditions? First of all, planarity, and then maybe even smooth. So we are interested in both cases. So if you relax the smooth condition and allow certain tropical singularities, one would be like very simple nodal singularities would allow such phases to occur. Even in the planar case, let's say we stick to the planar case, but we are interested in non-smooth ones. So there has been some interest. Obviously, such an enumeration is not that easy, because it's easier to look at all unimodular triangulation, at least in terms of softwares. You just have to add one parameter that you only want to look at unimodular. But once you allow such faces, then you are, first of all, not a triangulation and not smooth. So looking out won't be easy, but maybe for small genera we can try to compute, at least for, let's say, genus 3. So looking at non-smooth cases. And another aspect is to look at this forbidden criteria analysis, but in the lens of, as I mentioned, this modelized space structure, because there has been recent interest in studying the topology of the space. And turns out you have to categorize. So these graphs get stratified in certain ways, and we want to see if that corresponds to some sort of R classification that we get in terms of different criterias. Could it be related to those? However, our study is restricted to smooth, but such restriction is not present, but there might be some connections to look into. So these are some of the things that we are currently interested or talking about. And also um, so the another takeaway just to mention about this big phase graph is this is the only criteria that doesn't involve any cut edges. So it's all the criteria usually involve a cut edge and building upon this connection between cut edges and splits and likewise. But with this first of all incorporated a new technique, a new study about lattice polygons, and was also able to provide us with a criteria which does not involve a cut edge. Likewise, we also want to delve into providing criteria which look at regularity. So in all the criteria that we mentioned, nowhere we were able to show wherein we are using regularity, which is a very strong case. Not all essentially tilings of a polygon need to be regular. So one interesting case could be is to consider like a non-regular triangulation and look out if that can uniquely realize a certain graph, meaning that a graph that is only realized by a non-regular triangulation but is never realized by a regular triangulation. Such an example would be really nice to have, because that in itself would bring in this regularity into picture, which is a special condition in many ways for a subdivision to be regular. So I guess this is what I wanted to talk about, and these are just some of the references. So this is the one paper that sort of started the progress in this topic, and then this is the one that provided the classification up to genus 5, and this is the paper talking about panoptigons and big phase graphs, and this is just the one that got published last month. So this just pushes the case to genus 6, and as I mentioned, yeah, I'm thinking about chessboards and lattice visibility as well. So this is something, the work is in progress. So yeah, thanks a lot, and I'll be happy to answer questions.